Welcome to our final lesson in Unit 4. This one's about balancing redox equations. So before we start, I just want to recap to make sure that everybody's on the same page here. Remember when we talk about oxidation reduction reactions, we're talking about how electrons are transferred during a reaction. And we keep track of those transfers using a man-made construct called oxidation states or oxidation numbers. That's not actually how electrons are transferred or how they move about during a reaction. It's just the way that we can model how it occurs as human beings, and we have completely made up the method or the system by which that happens or the way that we record it. So now we're going to balance these redox equations. It's a little bit different than how we normally balance equations, but I think it'll make sense once you see how it all happens. Now, the first thing that you need to know is what a half reaction is. Now, we talked about things being oxidized and being reduced. If we take a full chemical reaction and we split it in half based on what's oxidized and what's reduced, we get a half reaction, and I'll show you that in just a minute. Then you'll see that there are several steps that we'll need to follow, and I'm just going to briefly read through them, but really they don't make sense until you start doing it. So I cannot emphasize enough the need to practice balancing these redox reactions. All right, so step one, we're going to write separate equations for the oxidation and reduction half reactions. Step two, there's a lot going on in step two. We need to balance all of our elements just like we normally do in a balanced reaction, except for hydrogen and oxygen. They're the exceptions to that rule. We're going to balance those using oxygen or using water to balance the oxygen and using hydrogen ions to balance the hydrogens. It'll make more sense once you see it. Then we're going to balance the charge using electrons. We'll multiply each half reaction by integers to get electrons to cancel out. We'll add the half reactions together, cancel out identical species, and then check to make sure that all the elements and charges are balanced. I know I just made it sound like, oh, this is no big deal. It is kind of complicated, I'm not going to lie. But like I said, if you practice, it'll become second nature and it'll make a lot more sense to you. So, as I said, the best way to show you how to do this is by doing a problem itself. So we're going to take a look at this first problem. We have manganese oxide ions, some iron ions, and they're going to form some manganese and some iron. Now, before you freak out, I know that there isn't oxygen on the right side of the equation, and that's something you haven't run into before. There will be oxygen over there once we start dealing with those steps that I just read through, so just be patient. The first thing you want to do is split these into half reactions, an oxidation reaction, a reduction reaction. In order to do that, we need to assign oxidation states. So we always know that oxygen's a -2. We know that when we have ions, the charges that are given to the ions are their oxidation states. So the only one we really have to figure out here is manganese. And how do we figure that out? Well, we have 4 -2's, which gives us a -8. Total, we want it to equal -1, which means that manganese had to start as a +7. So now we have to split this into an oxidation reaction and a reduction reaction. Here's a hint. You don't actually need to know which is which. However, for labeling purposes, it is kind of nice to know which one's being oxidized and which one's being reduced. So let's do the oxidation reaction first. Oxidation is the loss of electrons, and if you're losing electrons, you're becoming more positive. And so in this case, the Fe+2 going to the Fe+3 is being oxidized. Then we need to deal with the reduction reaction. And now I'm going to leave me some space here on purpose. You'll see why in just a moment. But that reduction reaction then is the manganese oxide ion. That's gaining electrons, so it's becoming more negative, going to Mn+2. So let's go up to our steps. Step 1, write separate equations for oxidation and reduction half reactions. As I said, you don't actually need to know which is which, but you do need to be able to separate them. Now let's go on to number 2. In each reaction, balance all the elements except for hydrogen and oxygen. All right. Well, we have 1 iron on the left, 1 iron on the right. So that's balanced. One manganese on the left, one manganese on the right. Balanced, done. So that part's done. Now it says balance oxygen using water and balance hydrogen using hydrogen ions. All right, there is no oxygen or hydrogen in the oxidation reaction from the iron, but there is in the manganese reaction. So we have 4 oxygens on the left side, which means we're going to add 4 waters to the right side. Then we need to take those 8 H's that we just added on, and we need to add 8 H pluses to the opposite side. I know it's strange. I know it makes very little sense. There's an explanation for it, but it's really neither here nor there. You really don't need to know what that explanation is. But let me just take here, let me rewrite the 8 so it makes more sense. So we added water to get the oxygens to cancel out. We added hydrogen ions to get the hydrogens to cancel out. So we did that part. Now it says we need to balance the charge using electrons. So let's start with the oxidation one. There is +2 charge on the left side, that +2 coming from the iron. There's a +3 charge on the right side. Now if we're going to use electrons, we have to keep in mind that electrons will reduce the total net charge because they are negatively charged. So we are going to add 1 electron to the right side of this equation. That means we have a net charge of +2 on the left side, and we have a net charge of +2 on the right side. Then if we go down to the next one, this gets a little sketchier. We have 8 H pluses. That means we have 8 pluses and 1 minus. So 8 pluses and 1 minus means we have +7 on the left side. Currently, we only have +2 on the right side. So we need to add electrons. Remember that we have to add negatives to make the left side more negative to get it closer to that +2. How do we do that? We add 5 electrons because if we subtract 5, that gives us +2 on both sides. All right? So, one thing that you could do at this point in time is check yourself. Let me show you something here. The way that I tell students to check themselves is that as they're working on this, they should be able to notice that electrons should show up on both sides of the equation. So in other words, in one of the equations, you should have electrons on the left side, and on the other equation, you should have them on the right side. Sorry, I just said that backwards. Right side for one, left side for the other. So if you have electrons being added to both sides, then that means that you have an oxidation reaction and a reduction reaction and that you're thinking about it properly. Okay, let's go back up to our list here. So we balanced using electrons. Now it says multiply each half reaction by an integer to get electrons to cancel out. Okay, so we have 1 electron on the right side in the oxidation reaction. We have 5 electrons on the left side in the reduction reaction. We need to get it to be 5 and 5. So in order to do that, and I'm just going to change color so it's easier for you guys to look at. In order to do that, we're going to take this top equation and we're going to multiply it by 5. Because if we multiply it by 5, that means we're going to have 5 electrons on the right side. Okay, so now we're going to work with that new equation. And we have 5 electrons on the right in the oxidation equation. We have 5 electrons on the left in the reduction equation. We now have succeeded in doing number 3. Now it says add the half reactions and then cancel out identical species. So let's add these together. It's kind of like adding 2 algebraic equations. Whatever's on the left on both equations stays on the left. Whatever's on the right of both equations stays on the right. So we're going to take, I'm just going to draw a line because we're going to add them together. We're going to take 8 H pluses plus MnO4 minus plus 5 electrons plus 5 Fe plus 2, those coming from that top equation, gives us, now here's another warning, these equations oftentimes run into two separate lines. In order to record that better, what I usually do is I stop where the arrow is. I start my next line with the right side of the equation. So 5 Fe plus 3 plus 5 electrons plus Mn plus 2 plus 4 waters. All right, now it says to cancel out things that are the same on both sides. Our 5 electrons should be the same on both sides, and honestly, that's probably it. So let's just rewrite this equation to make sure that we have everything down that we need to have down. It does not matter what order you write things in, as long as whatever's on the right side of the equation up above stays on the right side and whatever's on the left side stays on the left side. So you'll notice here I chose to put the iron last on the left side and first on the right side. It really doesn't matter. So now we're going to go back up to our last step. And it says to check to make sure that the elements and charges are balanced. So now we're going to do our checking on this. So let me just grab a highlighter here so that we can actually check what we're doing. We should have 8 H's on the left, and you'll notice that we have 8 H's on the right. 1 Mn, 1 Mn. 4 O's, 4 O's. 5 Fe's, 5 Fe's. So all of our elements balance out. Now let's take a look at the charge. We have 8 pluses, 1 negative electron, and another 10 pluses from the Fe. So these come from the H's. This comes from the MnO4 minus. This comes from the 5 Fe plus 2. All right. On the other side, we want to make sure that it equals the 5 times the plus 3 that comes from our Fe plus 3. We have another 2 that comes from our Mn plus 2. Sorry, I didn't mean to put another one in there. And then water carries no charge, so that doesn't matter. So let's add them up. We have 18 positives plus 10 positives. 8 positive plus 10 positives is 18 positives. Minus 1 gives us 17 positives. 15 positives plus 2 positives give us 17 positives. They equal each other, so that equation is balanced. Notice they don't have to equal 0, they just have to equal each other.